tree diagrams, and we're going to continue to do that today. It's just going to be a little bit different because we're actually going to be working kind of backwards through the tree diagram. So this is section 8.4, and we're going to learn a theorem called Bayes' theorem. And Bayes' theorem just talks about kind of how you handle it when you know the result already, and then you're finding the probability of where the information originated from. So this is used when the result is known. And we want to know where the data originated from. So like I said before, it is used for working backwards through a tree diagram. And remember, a tree diagram is just a visual way to organize multiple events anyway. And so here is the formula for Bayes' theorem. So it's the probability of A given D. Okay. Now, before I tell you what the formula is, it kind of goes in alphabetical order as far as order of events. So what this means is we already know that the final event D occurred, and we want to know the probability that it came from A as opposed to some of the other locations. So the formula for this is the probability of the first thing times the probability of the second given the first thing, and then all over the probability of the second thing. Okay, so we're just going to start off with a tree diagram kind of like we looked at in the last class. So let's say we have a decision to make first off, A or B. And the chances we choose A is 0.4 and the chances we choose B is 0.6. And then let's say that we're going to choose either D or what? How do we read this again? D with a little mark? Yeah, not D. And then same here. We can have D or not D. So some of the questions I'm going to ask you are from last class. But then we're going to focus on the new stuff too. So what's the probability of A? That's just a you can read the tree diagram answer. What's the chances we went A? 0.4. So what about the probability of A and D? So hopefully you're starting to learn the symbols a little bit better, okay? The formula for A and D is the probability of A times the probability of D given A. So we already figured out the probability of A, that was 0.4. Okay, so then how do I read this? The probability of D given A, what that means is we're given to already be here. So what's the chances that we then went, oh, I guess I need to give you probabilities, huh? Duh. That would be kind of helpful. So let's set up the rest of the tree diagram. I got kind of ahead of myself there. Okay. Notice that the values can be anything as long as each branch adds up to what again? 1. Okay. So now that we have values, this will be an easier question to answer, right? So if you're already here, what's the chances that we went D according to what I just wrote? 0.2. Okay. And if you multiply those together, you get 0.08. So what about the probability of B and D? And I'm asking you these things for a reason, because they're going to help us with the final thing that I want to know. So B and D would mean first we choose B, and then after that we choose D, right, given that we've already chosen B. So same process, right? We're just going, I'm going to point it with my fingers. We're going this way, and then we're choosing this after that, right? So what's the chance that we go B? 0.6. And then the chance that once we're here, we then choose D as opposed to not D is what? 0.25. So if you work that out, you get 0.15. So I'm going to space this over here because we're going to need some room for this. So I'm going to put a star by this because this is the new thing. So what's the probability that we started at A, given that we ended up at B? Okay, so before we use our new formula, I want to talk about kind of what that means. That means you already know you ended up here or here. We already know our result was D, but we're not sure where we originated from, right? Because how many ways are there to get to D? 2, right? We could go A followed by D, but we could also go what? B followed by D, okay? And so the formula is probability of the first thing times probability of the second thing given the first thing all over the probability of the second thing. Okay, so notice I already did the top, right? I already did the top in part B. Okay, so that is what? What did I get for that? 0.8, or sorry, 0.08. So then I need the probability that I get D, but notice there's 2 ways to get to D, right? I could go A and D, but I could go B followed by D. But I did both of those already. So what could I do with these since both of these result in D? I just need to do what with them? Add them, yes. I don't know why I can't write what I want to write here. My brain is not working the same speed as my writing hand. So yes, I want to add these, okay? And make sure when you punch these in the calculator that you put parentheses around that, okay? You would not cancel out the 0.08s. You have to actually add first. But this works out to be about 0.35. Okay, so there's about a 35% chance that if we already know our result in the end was D, that it originated from A as opposed to B. All right, so let's do another one. So let's do one with maybe 3 choices to begin with. Most of the time you're going to see probabilities written as percentages, but you can also see them as fractions. And there's no problem with these as long as each branch, again, adds up to what? Adds up to 1, okay? So let's say that this branches off into D versus not D for all 3 choices. So let's say this is a 1 out of 4 chance, this is a 1 out of 2 chance, and this is a 1 out of 3 chance. Okay. What does that mean about the not D's for everything? They always have to add up to 1, right? So what's this one going to have to be? 3 out of 4. This one's going to have to be 1 out of 2. What about this one? 2 out of 3. Okay. So don't let the fact that there's fractions in this tree diagram throw you off. Okay. It means the same thing. And we're just going to keep them in fraction form. So let's answer a few questions on this one too. So let's find the probability of A followed by D. So that would be the probability of A first, and then the probability that D got chosen if we already know that A got chosen. Okay? So don't make that harder than it needs to be. Just follow that path through the tree diagram, right? So what 2 fractions will you combine together? You're going A followed by D, so what 2 fractions is that? 1/3 followed by 1/4. And when we multiply fractions, remember we just do top times top, bottom times bottom. So multiplying fractions is actually Simpler than adding and subtracting them because we don't have to worry about a common denominator. What about B followed by D? That's going to be the probability that we go B, and then the probability that we go D after we've already gone the B route. So again, just follow that line through the tree diagram. And what two fractions do you get? You get 1/2 times what? 1/2, right, for a total of 1/4. So notice, I went here, and then I went here, right? So what about C and D? That would be the probability that we went C first, and then that we went D once we'd already done C. So that will be what? 1/6 times 1/3, or 1/18. All right, so we did kind of some pre-work, but this is really what I wanted to ask you. So I'm going to move it over here so it's still on the same page. If I want to know the probability of B, given that I know I end up at D. Okay, so in other words, I know the result is D. I want the probability that I originated from B instead of what two other options? Where else could I have originated from? A or C, right? But I want the probability that I did so from B instead. So remember that formula is probability of the first times the probability of the second given the first, all over the probability of the second. If you're wondering, you would get these formulas on a test. You would just have to know how to use them, okay? So any of the, especially the Bayes theorem, you would get given to you. So let's figure out what that would be. So the probability of B, we already did in the first part, right? Or in part B, I mean. So we got 1/4 for the probability of B times the probability of D given B. So if I want the probability of D, what do I need to do with these three things? Because those are the three ways to get to D, right? So what do I need to do with all three of them then? Add them. So again, just make sure you use your parentheses. Okay. So let me kind of show you what that looks like. And you can change it back to a fraction as well. So you've got 1/4 divided by 1/12 plus 1/4 plus 1/18. If you don't do it on a calculator, then you have to find a common denominator, and it's going to be a little messy. Okay, so push enter. What is it not liking? Oh, I accidentally put an extra symbol. So notice I said go to rather than just like, I said go to so that it would tell me where the problem was, and then I could just delete it. And so go to math fraction, and that's 9 out of 14. So if it's already in fraction form, go ahead and keep it in fraction form, but this comes out to be about 0.64. So there's a pretty decent chance that the origin was D, right? That's actually more than half, and we still have two other choices. Okay. Okay, so a lot of times we use this when we already know that we got a result that we want to track kind of where the result came from. So let me give you kind of some ways that you might use this. So it really doesn't matter what the topic is. We're just going to try to create a tree diagram to organize our data. All right, so let's say there's a new skin test for detecting tuberculosis. So this is going to be kind of wordy. A researcher studies 1,000 patients and finds that 8% of the 1,000 he studied tested positive for TB. But then let's say that each of the 1,000 people are also given a skin test. And the skin test is positive for 96% of those with TB. And then also 2% of those who don't have TB. So I want to know, what is the probability of a person not having TB, tuberculosis, but still getting a positive skin result? So I actually picked one that was a little wordy to kind of prove a point. There's a lot going on in this, and there's a lot of percentages being thrown at you. And so if you don't have a way to organize them, that can seem overwhelming and you don't really know which percentages to use kind of for what. So a tree diagram is perfect for this. So the first thing that they test for is whether or not they have tuberculosis or not. So we're going to use our symbols to literally say either TB was positive or TB was negative. Okay, so read through the data. How many people, what percentage of the people did it say tested positive? 8%, right? So we're going to say 0.08. So it didn't say so, but what does that mean about the not positive people then? How many percentage, or what percentage would that be? 92%. Okay, because every branch in the tree diagram has to add up to 1. Okay, so that's the first test they did, right? Does the person have tuberculosis or not? Okay, and then what was the second thing that they tested? Something about their skin. Notice I didn't really tell you what they were testing for, but that's not really important. So I'm just going to say the skin test was either positive or negative, like that. Okay, but then remember, these people also had a skin test. Everyone did. Okay, so what should go on the tuberculosis side for the people who tested positive? What was the percentage there? 96, which means how many were tested negative for that skin test? 4. And then what was the positive percentage for the people who did not have tuberculosis, but they did test positive for the skin result? 2, which means that what? 98 did not. So all the tree diagram does is just kind of formulates, organizes our data for us. Okay, so then notice the last question, the last sentence tells you what I'm asking for, right? I'm asking for the probability that a person did not have tuberculosis, given that we already know that they tested positive. Okay, that's literally what I asked you for in the last sentence, right? What's the probability that they don't have TB, given that they still got a positive skin test result? I know that looks weird, right? But I don't want to write it all out, positive skin test result. We'll just say skin or no skin. All right, so what's the formula? It's probability of the first thing times probability of the second thing given the first thing, all over the probability of the second thing. Notice how if you say it like that, it's not so weird to write it all out, right? So it's probability of the first times probability of the second given the first, all over the probability of the second. And we have percentages for all of these, right? So let's just kind of follow through with it. So what's the probability of going the not tuberculosis route, or of someone not having tuberculosis? 92%. So 0.92 goes here. Okay, then what's the chances that we, or that they then test positive? So we're already here, that's a given. So then what's the chances that they go here? 0.02. And then this one, there's a little bit more to it. Why? Because how many different groups of people can end up getting positive skin results? They can come this way and get positive, right? Or they can come this way and get positive. So what do we need to do with the two, basically? We need to add them up, right? So follow it with your finger if you need to, but we could go this route followed by skin. So it would be 0.08 times 0.92 plus, sorry, that should be 9 what? Not 9.2, but 9 what? 9.6. Or we could go this way followed by 0.02, so 0.92 times 0.02. I don't know if you've noticed it, but there's always a duplicate with something on the top and something on the bottom, but you don't cancel it out because we're supposed to do fractions first. So you would actually put a parentheses around the bottom if you wanted it to do correctly. So let's go ahead and punch that in. So it would be 0.92 times 0.02 divided by parentheses 0.08 times 0.96 plus 0.92 times 0.02. Notice I didn't use all my parentheses. I really didn't need them around every single decimal. It's just that I didn't want to use multiplication dots and get those confused with decimal points, so I just did everything surrounded its own parentheses. But when I enter it in the calculator, it's not really necessary. I can just use the times key. But notice, where did I leave the parentheses? Because you need this for sure. You need it around the whole bottom, right? Because clearly the bottom has more than one part. Anything with more than one part, we will need parentheses around. But it comes out to be about 0.19. Okay. In other words, if we're changing it to a decimal, or sorry, a percentage, it would be about 19.33%. So let me slide that over. Okay. So if you ask me, that's actually kind of a high percentage if you think about it. Okay. So that means if you were trying to use, because what they're trying to say is they're trying to use different means for testing for tuberculosis. I don't know if you know this, but the test for tuberculosis is very invasive. It's very ugly. And so what they're trying to do is, like, can we do something else and test to see if they have tuberculosis? So they were trying to use probably a nicer skin test where they could just observe your skin. But the problem is that people are going to get positive results when they don't actually have it quite often, right? So that would mean it's not very reliable. So like you would get a positive skin result if this were a real thing, and you would be like, oh crap, I have a really good chance of having tuberculosis, when actually you didn't have it, right? So 20% of people would be like unnecessarily freaked out, if that makes sense. Okay, so, all right, so let's look at another application, a non-medical application. So this is probably one of the more common formats that we use Bayes' theorem for in business scenarios. So people in production sometimes, or just in management kind of trying to monitor production, often want to track how many units are defective of whatever it is they're making. So let's say that a company has 3 plants that are making some item, A, B, and C, and let's say 35% of the products come from plant A, 35% from plant B, and the rest from plant C. So let's say that the defective rate for products is 1.5% for plant A, 1% for plant B, and 2% for plant A, or for plant C. So given that management finds a part that is defective, so given that a part is defective, I want you to tell me what is the probability that it came from plant C. Okay, because what's the other options? It didn't have to come from plant C. What else could it, where else could it have originated? A or B, right? Okay, so we're going to come up with a tree diagram to organize all our data, and you just want to leave yourself some room because we're going to have to go 3 ways here. I have no idea why I wrote. It's like it's a Monday, but it's not. Wrote B twice. Don't really know why. All right, so if 35% came from plant A, we're going to write 0.35 here. We're going to write 0.35 here. I didn't specify what came from plant C, but you should be able to figure it out. How come? They have to add up to 1, right? So 35 and 35 is 0.70. So what must have come from plant C then? 0.30. Okay. And then the choice is when you test a part, it's either defective or not for each plant. So the defective rate for plant A is, be careful about your decimal points. It should be 0.015, right? Not 0.15, because that would be 15%. So the non-defective rate is 0.985. The defective rate here is 0.01. So the non-defective rate is 0.99. And then the defective rate here is 0.02. So the non-defective rate is 0.98. So first, make sure you know how to set that tree diagram up. So what are we trying to find the probability of? We're trying to find the probability that the part came from plant C, right? But what are we taking for granted, or what is our given statement? What is already true for sure? We know the part is what? Defective. We just want to know what the chances is that it originated from C instead of A or B. Okay, so notice, the reason we need Bayes' theorem for this is because we know the results, right? We're trying to go backwards through the tree diagram and figure out the chances that it came from A, B, or C. So it's probability of the second thing times probability of, probability of the first thing times probability of the second given the first, all over the probability of the second. So I'm going to have kind of a long fraction, and I know I'm going to have a long fraction because I have to add 3 things at the bottom. But as far as the top goes, what's the probability of C? 0.30. And then the probability that once we're here we get a defective part is what? 0.02. So then what are we going to add? All the routes to get to a what kind of part? Defective, right? So we're going to add this times this, plus this times this, plus that times that. Okay, so it's going to be 0.35 times 0.015 plus 35 times 0.01 plus 0.30 times 0.02. So I want to show you how, if you want to, you can also do the fraction separately. And what I mean by that is you can actually do, figure out the top, write that down, and then figure out the bottom and write that down, and then divide them. If you seem to not be coming up with the answers that I am when you get home and try this on your own calculator, then you might want to think about doing something like this. And I forgot a 0, which is actually really, really important. So 0, that whiteout is really crappy. So notice what I get there, and then I can just divide it. So 0.006 divided by 0.01475. And so we end up getting about 0.407. I'm not necessarily being very consistent with how many decimal places I'm putting, but just know that my math lab is going to tell you how many it wants. Okay? On a test, I'll tell you how many I want. So don't worry too much about that. So basically, like, when do you use Bayes' theorem then, as opposed to some of our other stuff? Yeah. So note, we use the Bayes' theorem formula when you know the result or when working backwards through a tree diagram. And I wanted to say that again because on the test you're going to have to be able to figure out, is it a normal tree diagram question or am I trying to work backwards here? Okay, because we only use this formula when we're working backwards.
That confused me for a minute, 'cause I'm like, we're doing the exact same thing as that.
Yeah, it's just a little opposite, honestly. Like, you know the result and you're trying to work backwards. Okay. So believe it or not, a lot of times, so let's kind of go back to this last example. So if they have good bookkeeping practices, then this really shouldn't be an issue, right? That's why things have barcodes, and usually barcodes tell the company where it came from. But this is actually used a lot of times. For instance, have y'all been hearing, like, when food, like, don't buy, romaine lettuce because there's been E. coli or whatever. Well, you can't put a barcode on produce, right? So they actually have to do, some pretty high-level statistics to try to figure out and backtrack where that bad produce came from. Okay, did it come from, the farms in South America? Did it come from where? Okay, so they're trying to find out where it came from, of course, so that they can, stop the E. coli infections. So this does come into play, but it can be curbed if, companies that can put good barcodes on things. In other words, like, if I pick up a plant, if I'm making computer parts, I should be able to tell where that computer part came from if my company has coded it properly. So it should be able to be very obvious where it came from. But just practically speaking, that's not always necessary, or not always possible, not necessary. Okay, so that's really all for Bayes' theorem.